Like biological neurons, a plausible data structure should be able to store and relate any kind of information without limited predefined data designs. Within the structure itself, we can make changes to the nodes and edges, including the link types of the various edges, unlike biological neurons. An example of this sort of flexible data structure can be seen by the sensory pod viewing an image of what we would call a basketball. The data from this image is stored as a visual thing, which can have nodes to various things like objects, shapes, etc. These nodes can also have edges to other various nodes. This allows for property nodes and links to be added whenever basketball is fired, like its color or size. Speaking of nodes and edges, each node can be thought of as a cluster of neurons within the brain. Each node can be connected to any other node by an edge, or in the biological sense, the connection between clusters of neurons that represent abstract things. Say there are two nodes which contain the information for blue and red, and each have edges with another node that represents the color information. If blue or red are fired, then so does color. In this, the direction of firing occurs one way over edges, like synapses across neurons, but in a bidirectional knowledge graph, there is a parent-child relationship. Like many biological models, including the Hebbian model, these can be directly applied to this sort of data structure as well. Though not all relationships will be of the parent-child sort, there can be reference relationships, or reference-by relationships, etc. Many facets of the data structure are biologically plausible. For biological systems, there is a maximum number of neurons and synaptic connections between all the other neurons. A graphical structure can be scaled to any size needed with relative ease on modern computers. Recently, a system of about 2.5 billion nodes and edges were clocked to fire in less than a second. Lastly, a useful AGI system will need to make computations and decisions on at least a similar timescale to humans.
Hello, I'm Shimon, and I want to present to you my paper. Two models are proposed. One is based on deep learning, trying to reach high cognitive functions, and the second is mainly based on psychology and sociology. We start with the deep learning model. Inspired by Jeff Hawking's predict structure of the human neocortex, we turned it into discriminative generative structure, or the encoder-decoder structure. Or in more details, we encode all possible information coming from text and vision, finally into some extracted features that represents the whole situation. And upsample it to the actuators for a proper response. Now we'll see different components and their possible implementations that exist in literature. The first part is extracting features separately from sensors and text. This part is inspired by image captioning test. Then we extract these joint features further into longer timescale tasks by using intermediate tasks. These tasks are intended to recognize relationships between perceived objects. Some papers focus on pairwise interactions, while others focus on higher order interactions. These relationships or actions are spread over different timescales. These hierarchical temporal RNNs can be implemented via different clock rates, or via sliding or shifted LSTM blocks, or via dilated causal convolution. We see that the decoder is also hierarchically temporally constructed as a minor image of the perceptual encoder, with skip connections, which can be, for example, copy or normalization, addition, and more. Now we describe briefly the training phases. First, it learns to fuse multimodal inputs to establish basic semantic concepts. Then it starts by learning basic elements, objects, and then continue with composite objects and relations. After this proper symbolic comprehension, it turns to learn how to respond correctly within the common supervised learning approach. Just as in the encoder training, here it performed also gradually, from short to long-term tasks. Now we go over some details regarding phases 2 and 3. Inspired by these implementations, we propose to do similarly here. In the upper left corner is a snapshot of our system, and in the middle is its equivalence in image captioning system. The right top describes the inner structure of the RNN in a folded and unfolded forms. Step 2 is actually sending the hidden state of the first layer of RNN to some decoder for some supervised task, referred here as intermediate task, in order to learn the embedding in matrices U and V. Step 3, using these embeddings to produce outputs for the next layer of the RNN. Now back to the third phase. We illustrate how gradual learning is done. Each time we proceed to higher level, the lower levels are freezed, while the more higher level do not participate in training. Now we can view this idea better in 3 dimensions. Here we see fast tasks, meaning fast input with fast reactions. Slow tasks allow a slower processing of the incoming information, while gaining control over the fast tasks by constraining their action. When higher tasks are operating, they decide upon the more restrictive actions available for the lower tasks executions. We also have skip connections for the lower level to allow it to continue operating almost independently. Specifically, the connection that fast tasks had in previous slide. Next layers operate in the same fashion. This resembles the biology-based approach where after repeating some task, it becomes automatic for us such that our mind is free from concentrating upon it and now can deal with other tasks while performing these low-level tasks. This potentially can introduce also working memory or thinking in higher available layers to solve difficult tasks. How is it possible? Because the inputs are very slow or stable. So these layers don't need to process the fast tasks. So they left to deal with the harder tasks provided in the text input. The round plate represents these possible cognitive functions. Now we represent our second model, the Associative Knowledge Representation Model, or in short, AKRA. It deals with several types of memories, short, long, and working one. And it is based mainly on our communication model, as will be described now. We start with the assumption that our inner models of the world are totally different. We argue that each of us is like a black box with respect to the others, and it is expressed via low quality of communication, resulting with misunderstandings. Black box principle isn't appropriate only for human intelligence, but also for AI. Assuming that AI's internal perception cannot be directly interpreted by us, it must undergo over some means of communication. All this section about communication with the AI emphasizes my opinion about black box issue people have with deep learning. My thought is that logic and interpretability is the outcome of neural networks. Hence, neural networks probably were designed by nature to be unexplainable, since explainability is an expression of intelligence, but not its vessel. Therefore, we can reason and understand AI only through communication with it, not via analyzing its internal structure. The basic assumption here is that communication must be logical and consistent, along with other communicative characteristics. We can imagine ourselves what mental image a person has before he turns it into words and passing it to some recipient. Here's some examples for that. A description of composing Lego elements, a description of a dog doing something, or a simple description of an elephant. It can be any type of message, such as story, how to do something, and more. Anyway, despite the agreeable communication between us, the interpretability of each of us is different and subjective. It is due to different perception or world models each of us has, models of ourselves and also of others. Hence, sometimes the difference between the original message to the perceived one can be in the range from small to huge, where misunderstanding starts to occur. And even worse, none of the percipients are aware of this happening. We can even extend the number of models we have for even ourselves, such as different ways we behave and express ourselves with different people or within different surroundings, and so on. Since all of us are in different state of mind all the time, we must eliminate this gap by starting our message in the most general form and gradually lead the listener to our specific and accurate message. Hence, we start the message generally and end it with specificity. Similarly, this presentation must be constructed consistently for the audience to understand it. For better communication, especially for the common sense or the lots of unspoken information, both the recipients and the sender must have models of themselves and others. Expanding the modeling for communication we have seen previously, we can infer that we actually modeling everything, each thing depending on our interaction with it, which could also be passive, such as by observing or mimicking, or active. It applies to ourselves, to different people with different interactions, and to different groups of people. Similarly, it applies to each object or group of objects, and similarly, it applies to animals. Now we go into some details. Based on some of the communication principles we have seen so far, we can derive acron, expressing how information is represented in the memory, and to serve as a basis for cognition. We demonstrate how associative memory is generated in a hierarchical form from a sequence of phrases or sentences. Here we start from some phrase, next one, and the next one, and the next one, and then suddenly it's a different kind of event. So we can ask ourselves, what is common to this previous group? And we summarize it. Now we continue in the same fashion. Again, a new event, but we will continue in a less detailed form. Now we go over to retrieval. This representation is also comfortable to examine comprehension. For example, asking questions about the message that we received or a story as we've seen just now. Here, for example, a question. And now we'll see how we move along this hierarchy. You first search in the highest levels, then in the relevant episode you search in its lower levels, till you find what you need. Please note that we look mostly in the lower levels because the descriptions written in the higher ones are misleading. It is not representing a sentence, but the essence of facts in the lower levels. It is actually a speechless representation of a grouping of the lower levels. Here's another example. As you can see, the trajectories can be back and forth in any order. Now we can view it more generally. In order to both generate a hierarchy from a sequence or vice versa, some kind of order has to be stored. For example, chronological or causal one. And it has to be in all the levels of the plot. See, for example, the temporal trail in the top view figure. The lowest level contains most common used triggered concepts or events, which are associated to a huge amount of hierarchies. The higher you go in a given hierarchy, the more specific the message becomes, and it is more differentiated from other hierarchies. Here's a side view of this hierarchy. We can see in the top written working memory, but another model can be where the whole hierarchy is inside the working memory. And the top is simply the hierarchy's essence. The trigger terms that construct the lowest levels of any hierarchy can be, for example, triggered neurons in the DLM presented earlier. Or it could be the perceived embeddings in the highest temporal levels in the DLM. Now we talk a bit about the memory organization or structure. We can assume that simple sensory perception is using base memory similar to system 0, automatic system, no thinking system. Then it provokes long-term memory concepts or events, uploading it to the working memory. And at sleeping period, the system somehow decides what to consolidate into long-term memory and what not, due to unimportance or similar memories already exist. Note that the long-term memory and the working memory are not connected to the census and the executions. Perhaps, since this is the abstract thinking, where thinking, depending on some tests or some external instruction, is moving in a purposeful trajectories, mostly or sometimes regardless to the inputs. Actually, we assume that there's a permanent associative wandering in long-term memory, which produces some final or intermediate results which are updated in working memory. All this wandering must have some purpose, as mentioned earlier. So there's some external will inserted in this process, guiding it. My belief is that we solve any situation or problem this way, by simply jumping associatively from hierarchy to hierarchy, or within hierarchy, along with some guiding will, which is about searching for something, gathering some intermediate insights to eventually resolve with some response, which could be, for example, good solution or bad solution or no solution at all. Actually, we can regard the base memory simple as part of the long-term memory, to be as the most frequent used in long-term memory, almost automatic. Thank you for listening.
Hello, everyone. My name is Kristina Sarkisyan, and I would like to present our work graph strategy for interpretable visual question answering. We are going to discuss the visual question answering task, the interpretable VK task statement, our approach graph strategy Decay model, and then move to experiments and results. Visual question answering task assumes an answer to a natural language question about a given image. It is a very important task since many visual language tasks can be reduced to it. Decay requires a rich understanding of both the visual content of images and the textual content of questions, so it unifies several research areas, including computer vision, natural language processing, and knowledge representation and reasoning. Decay systems have the variety of real-life applications, like medical diagnosis, visually impaired people aid, anomalous situations detection, and others. That is why Decay systems require reliability of the predicted answer and robustness. This leads us to the problem of an interpretable Decay. Existing deep learning and other black box approaches make it difficult to trace models' decisions and reasoning process. Moreover, such approaches often rely on different biases in the data. So our aim was to solve the Decay task in an interpretable way. The interpretable Decay task is formulated as a development of an interpretable model capable of predicting the correct answer to the question, given the input image and the question. The main idea behind our model is that it uses a strategy based on the question text. This strategy, using a set of special rules, transforms the initial description of the image into the final state, leading to the answer to the question. As a strategy, we consider the recursive traversal of the question's graph representation, in which nodes represent the objects mentioned in the text of the question, and the edges are the relationships between the objects. The rules are responsible for applying the appropriate estimator to the seen objects. that is either one or a set of models with trainable weights, designed to define queried properties and relationships of scene objects. So, along with models construction, our aim was to maximize the accuracy of the estimator's answers. Here is the schematic illustration of our graph strategy Decay model. The question is fed into the question-to-graph model, that is a sequence-to-sequence transformer, while the image is processed by the faster RCNN object detector. The answering procedure implements the strategy. Having received a graph representation and a set of objects as input, it performs the graph traversal with a successive call of the estimators to check if the scene object matches the node's characteristics. The final state corresponds to a graph where all nodes are assigned to objects. Let us consider the step-by-step example of Gsvk question answering process. We have an image question pair. First, the question is processed by the question-to-graph model that is trained to translate the natural language text into the graph representation. This model extracts the entities from question text and the relationships between them, and maps them with graph nodes. So we obtained the graph, and the queried property is object's material from the deepest node. The image is processed by the object detector that produces the bounding boxes of scene objects. Then the graph traversal begins from the first node. Each object property from candidate object set is checked by calling the required estimator within a procedure. For this node, we check object sizes and colors. The objects that suit node's characteristics are assigned to this node and form current node object set. Then we start to check other objects, whether they are in the required relationship with the current node objects. These objects form the candidate object set for the next node. This process is repeated for each node until we find the deepest node's object and extract its material using appropriate estimator. The answer to this question is metal. Thus, the model provides not only an answer to the question, but also an interpretable explanation that illustrates the relationship of scene objects with objects mentioned in the question's text. In addition, the obtained history of scene states allows us to trace the reasoning process. There are two versions of Gsvk model. In the first version, we use multiple estimators with different architectures and input formats. For example, for question answering on clever dataset, we trained 8 estimators. For color, material, and shape prediction, we used convolutional networks, while for size and spatial relations, we used multi-layer perceptrons. Each estimator is trained separately on different data, which can be a laborious task for a large number of objects' attributes. That is why in the second version of model Gsvk v2, we propose replacing multiple estimators with one trainable unified estimator that performs similar functions but is trained once to simplify the estimator's training process. As a unified estimator, we consider VL-BERT model that works with textual and visual data and can be adapted for different visual linguistic tasks. We validate the Gsvk model on 2 datasets. The first one is Clever. Clever is a synthetic decay dataset that contains images of 3D rendered objects and compositional questions. A scene object can be characterized by its shape, material, color, and size. There are 4 types of spatial relations and the relation of equality or inequality. The 4 visual question answering dataset was generated in a near photorealistic 3D environment AI2Thor. For question generation, 25 kitchen scenes and 36 types of objects were used. In experiments, we used 3 types of questions that are existence, preposition, and material. Here are the accuracy results on the Clever and Jsvk datasets. We compare our model with state-of-the-art models, which are Sjvk and Untitled. The Gsvk model demonstrates results comparable to the state-of-the-art, and Gsvk v2 outperforms the first version of the model. For Sjvk, we used CNN ball model as a baseline. The Gsvk model archives the close score on material questions and drastically improves results on other questions types. We assume that a better object detector would further boost the performance. To summarize, our approach decomposes a complex compositional question into a sequence of simple questions. Gsvk maintains transparency and interpretability of the response generation process. And the unified estimator simplifies the model training procedure since it maintains a single format for input and output data, regardless of the attribute type, and is trained for all attributes. The unified estimator can be useful for generalizing on new unseen data, for example, using zero-shot models. The problem of adapting Gsvk to real-life decay datasets is considered as further research. Thank you for your attention.
Hello, my name is Shimon, and I want to present you my paper, Dynamic and Evolving Neural Network for Event Discrimination. First, I want to present my Agi model very briefly, just an architecture. It is inspired by a neural model of Jeff Hawkins from his first book. Here we see a side view sketch of the model and its top view diagram. As you can see, it is a hierarchical structure with some supervisor program that supervises the whole AGI and the working memory below, which fuses two modes, the visual and auditory modes. And each of them has its own processing unit that translates the inputs, the sensory inputs, to its unique memory. Now some Agi details. This Agi model is based on global working theory, since here it is also based on multiple agents or components. Additionally, one-dimensional information such as language has a shared memory for input, output, and working memory, denoted as 1D memory. This is also true for the multi-dimensional information. It is also based on stimulus-response behavioral theory, which states that the mind can be communicated with, although unobservable. This is why the black box. We have a stimulus and black box, and then response. The Agi itself should be adapting itself to the environment, meaning to be dynamic. Hence, it should interpret spatiotemporal objects or events. Object recognition or tracking or even scene understanding, like here, are all treated as frame-separated philosophy, while AGI should interpret events continuously, not as fragments. Hence, the deep learning model we propose is based on events as a whole, without separating the space from time, just like in the relativity theory of Einstein. In my earlier model, I thought that as we have two channels of input, vision and language, similarly, we can extend the design for AI to have these two channels also as outputs, so that we can see its inner thoughts. And then I wondered, why don't we humans have imaginary tool as output? One can argue it would hurt our basic desire for privacy. But then, as we choose whether to talk or not to talk, we can similarly choose when to turn this tool on and when to turn it off. My current opinion is that the world we see with our eyes is what we all agree upon. Other than that, our inner models of the world are totally different. And why we don't have symbolic or linguistic channel also objective as vision? Why we end up with inner individual and unique symbolic representation? I think it's because language is highly context dependent. And since each person has different contexts along his life or different experiences, then it develops in different meaning or different feeling or understanding of the objective concepts we are all agree upon. Concepts of a language that we use to communicate with each other. So the concepts we use in external communication are objective and common to all people, but their interpretation is different for each of us, depending on the specific sequence of experiences each one goes through. Therefore, physical reality is only for objective agreement for effective communication between us, which realized via language. However, vision is not a communicative channel for us. Now we present our Dnn model. We know the regular DNNs used for special object tasks, such as clustering or classification. But what if we want to detect and extract features also along the temporal dimension? Then we simply extend the DNN to include this dimension without changing the spatial dimension, meaning orthogonal to it or perpendicular to it. So in the following, the DNN we will see is spatio-temporal one. We can see here only the temporal dimension, and here we see both of them. Now we present some assumptions about our DNN. First, we assume that the task is to identify events. Secondly, we assume that small amount of data should be represented by a small model. And similarly, big data should be represented by a large model. We can see here an example from a paper showing that performance is a function of the data. Also, by gradualism, we mean that we assume that the AGI generally, or in this case, our DNN specifically, should be growing along with its experience with the world. It should grow internally. And following that, the complexity it encounters should also grow accordingly. The growing itself should be based on experiences, meaning it is embedded in the perceiving experiences of the DNN. In other words, in the visitations over neurons and weights. For example, by counting these visitations or occurrences. Based on these assumptions, we propose our evolving DNN, demonstrating it like a newborn infant perceiving its environment. But before we start, we just want to mention that we assume that the DNN is perceiving and updating its weights according to the deep learning methodology, meaning a feed-forward perception and backpropagating weight adaptation. Only the difference is that in addition, we assume an external supervising algorithm that controls the changes in the DNN architectures, its structure. Now, the first thing we assume about an infant is that it learns unsupervised. He starts with a single event detection, as we can see here. Also, as you can see, we assume some initial deep neural network. So it doesn't start from an empty network. It has some initial structure. Now it can differentiate two events using the deep features in between. For example, day and night. And he can go on and recognize as many events as necessary. It is adaptive neural network structure, adaptive by necessity. At some point where strong connections and event identification is strengthened, it can move its attention to other stuff, or its sources are more free since the given level is more automatic for him. It can build a new floor if reoccurrence of events is detected. Thus, it is actually hierarchical multitask DNN. The composition, as you can see here, can be either a sequence of events or not a sequence. An opposite structure changing operation can be decomposing of an event, if it appears to be more complex than it was supposed to. Here we recognize that the ball in the air event is a composite event, so we decompose it to a simpler events. We can view it as a refinement. Additional information you can see in the paper. Some issues with the model, advantages, and related work coming from many fields in AI, such as continuous or lifelong learning, unsupervised learning, event detection, network architecture search, and growing network. Thank you for listening.
Hello everyone, in this video I will review current capabilities of our neural symbolic Minecraft agent. This agent possesses its own autonomous behavior, so it has started exploring the Minecraft world. It tries to find novel blocks and get novel items by mining them. In this demo it starts from scratch, so it can look like an unexperienced player, and it sees a lot of new stuff, so it can be a little bit confused. This experience can of course be incrementally accumulated and reused. It uses visual input. For example, it sees leaves, it sees logs, and so on. And it uses to navigate. In addition to the visual input, it uses some symbolic information, which is also accessible by a human player. So everything is fair. Visual input will also be used for detecting visually novel places for exploration, which we are working on now. But currently it just searches for novel blocks around, and when it sees no novel blocks, it starts searching by reallocating. As you can see, the agent has found already a bunch of blocks and items, so he is likely to found coal ore, and it continues to discover additional kind of blocks. It has gotten stone. For acting efficiently in the world, the agent needs some symbolic skills, and this behavior is heavily supported by these skills. It can continue searching for a very long time, for hours, although in a not a purposeful way. However, symbolic reasoning is also very important, which can better be seen if we ask the agent to do something concrete. Okay, so let's ask the agent to get some wooden door. Yeah, it has crafted a wooden door from oak planks. It was not lucky to have enough planks for this, and it can be considered like not too cool. So let's ask the agent to get, say, a wooden slab. And now it doesn't have enough planks, so it decides that it needs to mine some oak, and it got oak logs and created oak wooden slab, so everything is cool. Let's ask it to, say, get torch. It's again not a problem because the agent already has the necessary components, but if it didn't have them, then it would try to find. Similarly, we can ask it to get anything else. Okay, it's a lever. But let's try asking it to get something more difficult, like iron pickaxe. So what it is going to do in order to mine iron ore, it needs stone pickaxe. So it's a kind of instrumental behavior. It tries to acquire ingredients for the necessary tool. So it understands that it needs this tool first, and after this it will go and search for iron ore. It's much more difficult to find iron ore. I'm not sure if it will be successful in a limited amount of time. In any case, it should be understood that if we want the agent to achieve arbitrary goals, we need it to possess compositional behavior. So it doesn't know what exactly we will ask it to do. The reason the agent reasons what intermediate steps it has to perform depending on the current situation in order to achieve the goal. The situation can change while the agent is trying to achieve the goal, so it should be aware of the changing circumstances in order not to follow the possibly obsolete plan blindly. Or the agent may not know yet where to find certain blocks or ingredients, so it will need to search and explore. As you can see, the agent can achieve different goals from different starting points. It doesn't simply follow an imperative script or demonstrates a reflex-like single-way behavior typical for deep learning, deep reinforcement learning systems. Such compositionality and robustness needs tight symbolic-sub-symbolic integration. Okay, so I'd like to emphasize that this is not the final version of the agent, but it's the very beginning. The interesting part is just starting. We need the agent to learn on its own, both on symbolic and sub-symbolic levels, to explore the world deeper and wider, to construct, to farm, to interact with mobs, to collaborate with other agents. Such an integral activity is difficult to imagine without Agi technologies. That's why we consider it as a good testbed for our approach to Agi and its implementation in the Hyperon architecture, which is under development now. So we can try waiting a little bit and see if the agent will be successful or not. Or we are lucky, so it has found some iron ore exactly when we need it. So the agent has successfully created an iron pickaxe. Thank you, and hope to provide you updates soon about more Agi stuff.
Hello, my name is Pieter de Doest, and I would like to give a presentation about my paper, the Delta Normal AGI. What is it about? Well, the Delta Normal AGI refers to Ben Goertzel's paper, The General Theory of General Intelligence, and that paper can be found on Archive. Possible use cases for the AGI are, for instance, web shop content generation and, for instance, care home social companion software. The AGI makes use of certain basic principles, as can be found in this list. The starting point of the Delta Normal AGI is that it's all about problem solving in dialogues. And that is why the AGI is built around PSDs, problem-solving dialogues. Next to the PSDs, quarks are also essential. There's another important principle for the AGI, which is the evolution principle. So we have population, we have signal input, operation, and evaluation, and this goes in a loop. And this can also be done in a fractal or recursive manner. The AGI makes use of two basic important algorithms. The first I call lookup-add, and the second switch router. So if we take a look at the lookup-add algorithm, it looks up in a record table whether an entry exists. If it doesn't exist, it will add the entry to the same table. The similarity check is done based on quarks. So each element has a number of quarks associated with it, and then the algorithm will look whether there's overlap between the two quark populations. The second algorithm is based on the patch paradigm, which is that the total AGI has a certain amount of knowledge, and this can be divided up in patches. So each patch stands for a smaller amount of information, and the total of these patches gives again the total knowledge of the AGI. So how does the AGI obtain its information? Well, for this I make use of the TCAL mechanism from Monash University in Australia. TCAL stands for topic, explanation, evidence, comments, and link. So the AGI will ask, well, what is the topic? What is the goal? What is the evidence for the information I have or I get? And what are the comments on this information? And you can translate these steps to the different use cases. So for instance, for a care home, the AGI will ask the user, what is the topic? Or it will try to assess what the topic is. What is the goal? What is the evidence for the information I give to you or I get? And what comments can I deliver on this information? Then if we take a closer look at the PSD, the PSD actually is a COFO as defined by Goertzel. So if we have an element, this element is actually determined by different factors. So for instance, emotion, or the different TCAL components, or the drivers, or the previous element. And the quarks, of course, underlie all these elements. So then the next element is formed, and the total of the elements form a sentence. Another way of looking at this is that the PSD actually is a triangle form, and the lowest layer is the machine learning or sub-symbolic layer, and the higher we get, the closer to the target, the higher the information content level gets, and also the information gets more and more symbolic. And this total is of course then a layered model. The PSD is a fractal, so a total PSD can be made up of smaller PSDs, and the delta normal AGI is all about selecting and optimizing the best PSDs. So PSD stands for problem solving dialogue, and we can depict it as follows. So we have a delta axis in which the delta is the discrepancy from the target or from the normal information, and we have in this axis we have progress or time, if you will, and then in time the target gets reached, and the target has the highest information content level, ICL. You can compare this to the definition of Pai Wang, in which he says that intelligence is based on how to work with insufficient knowledge and resources. So this is also limited, the delta is limited, and the amount of time is limited, and in this time the information has to be built up. So the PSDs can be made up of different smaller PSDs, and for instance, to match, to balance, find, generate, control, all these different PSDs can be used as a sort of a blocks to make one bigger PSD. So now I would like to show you some of the code I've written. We give an input, for instance, hello, and then we get an output and it recognizes a class. Or if we input chair, it will recognize the Quark support. And if we then put in table, it also has the Quark support, so there is an overlap in the Quarks. If I would now say I feel bad, then it will recognize it as a problem, so I can choose the different sub-PSDs to solve my problem. Well, that is about it. So thank you for listening to my presentation, and if you have any questions, please let me know.
Hi, this is a presentation about enabling AGI agents as a framework for enabling that. What do we mean by a solution framework? A solution framework has some basic components. So we have the behavior that we want to control. We have the agent or the controller, sets targets, then some metrics are provided from the behavior, and then a deviation is provided based on the target from the targets, and that deviation is used to with a control mechanism to make control signal that will change the behavior. How this framework, example that is most relevant to us is communication theory. At the time, again, the 50s, the system was known and the controller was known, the designer, and what control theory contribution and breakthrough came when it was identified what to measure and how to change those parameters. What to measure was the entropy or the information that was the frequency of the symbols and signals used in the communication. The source coding and channel coding both operate on that frequency. Source coding identifies that frequency, channel coding changes by adding redundancy to the signal, change that frequency. So identifying what to measure was key in understanding or closing that framework and make it work. So if we try to apply the same approach to intelligent systems, so the intelligent behavior is what we want to influence, then we need some intelligent metrics. We need to have a control signal. We need to have a controller that will determine what to do, and then we need to have a control mechanism. As with communication theory, what we think is the key metric to measure is how to select an action. Intelligent systems are really can be only, or intelligence in a system can be is only apparent when the system interacts with its environment or other systems, and if that environment it interacts with is changing. Those, I mean, there are other conditions, but for our purpose here, I think these are the most relevant, that it interacts. A system that sits and does not interact with its environment is very difficult to say, is it intelligent or not. The same, if the system is interacting with its environment and nothing changes, it's also difficult to say. So we think, or we propose, that to use how to measure the actions, how to measure the value in bits for an action, that will help identify the control mechanism and will help the agent to make the control of the behavior. So there are three aspects to that. I mean, how many bits are required to take an action, and then how taking an action will change the overall bit value for that action in the future, and then how that choice for a certain action will change the entire balance, the entire information of the system. What we propose here is for in communication theory defined information related to the frequency of an event. What we are proposing here is to define information in indication of a connection between two events. So here an event can happen or not happen according to some probabilities. Here, we measure this for a connection between a relationship between two events. So when we talk about a relationship, means we need one or more events. There is no relation without two events at least. And that is the difference between the definition we are adapting here and that of communication theory. So again, we are talking about relationships between events or entities or features or parameters, and not about the parameters themselves. How would that work now when we try to see or calculate the information for each connection? So we have an example like this. So it's a kind of an organism or a based on previous experience. It meets or it encounters these objects in its environment, and then it either eats it or keep it, store it for later, avoid it for whatever reason, or it doesn't know what to do with it. And over 100 objects, I mean, if you add up these kind of these numbers, will give you 100. So it met object A, encountered 8 times, sorry, and then 6 times those it kept it 2 times. It figured out it need to avoid that one, and so on. So the question now, after the agent or the system have learned that, is always what to do when you meet one of these objects. That is one kind of questions, or how to maximize any of these, how to maximize the food, or maximize, I mean, increase the safety by maximizing the or conditioning on avoidance, or increase the energy intake by conditioning on the consumption. To answer this question, we then provide what we call base information. So this structure here is translated into this matrix, where the output is here and input, those are the different objects, and again that can be swapped, that makes no difference. And these are the entropies of the different connections. It is not the entropy of the different events, but of the connections. And if you take the number of bits for that, it will correspond to the frequency or the number of bits required for each of these connections between two events. And then we, in order to calculate a Bayes probability, we have to condition on one parameter. And here we conditioned on these two. So separately. So if we say, okay, I want to condition, I want to know the bearing, the impact of each of these inputs on the consumption. I mean, if I want to consume, what is, if I meet how much contribution do I get from yellow objects, how much from green objects, and that gives that first row. So the yellow, green, and these are not available because there are no connection. It never consumed the red object. That is, and that adds to 1, and that gives the probability by which each of these events participated or contributed to any one of these. But again, we have to condition on any one as required in Bayes calculation. Then the step that we went further and did is that we took that probability, and then again, I mean, the probability log that probability to base 2, and then provided what we call Bayes information. That is, again, the number of bits corresponding to this interaction, between, or if we condition on y, for example, so that gives the number of bits with which every input participates to that event that we condition on. What does that mean? It means that to select this event, we need 3.27 bits of information. To select this, sorry, it's the other way around. The W is the less one because it has less connections, so the selection here is less. And it is, again, it is in the same sense of, if you want to know how much information do you need to make that decision, this is the number of bits that will that is needed for that. Again, sorry, I keep mixing, but okay, it is written clearly. So that is what we provided. This is the first metric, is the value of each connection. Now the second one is the selection, how the selection impacts the future of that selection and the entire interaction. So that these are different distributions, I mean, and that the selections are maximum is that it is 1-to-1. So really the information we need is I mean 0 and 1. So it's a straightforward. If we condition on W, it is only B, very clear. So 25 cases or events goes to each one of the outputs. This is the case we looked at. This is the other extreme, is where every input is connected to every output almost with the same. I mean, those are 24 connection. That's why 4, 4, and then we have 5s to add to 100. And then we get a very regular distribution of the amount of information needed for every to make every choice here. As you can see, the same in the entropy for the entire interaction, the entire space of interactions. Here, because they are the frequency is very close, it is the highest entropy, and this is the minimum one. So with every new selection, all of these numbers change. Every new selection means next time, if I am at A and it happens that I took this route or this connection, not this connection, this number will change, will be 6, 3, and this would be the 101 encounter or event, and that will change the entire numbers in here slightly, but it will be traceable. And this is how we can trace how every choice impacts all of the other choices in the environment. So now, I mean, that was a simple case. To make it more complex, so that organism or object, it meets a lot of object, and they not only have color, they have shape, taste, texture, context, and then they have also different energy content, effort to obtain, sickness after they consume, and then effort to digest, for example. So this then, if we develop the same approach, we'll come to something like this. So again, the question is, if we want to condition on, if we have a low energy and want to increase that energy, so we will condition on low risk, high energy. So this will tell us, if we condition on those two, all of the different values of all of these inputs, how do they relate to these two conditions? And that should help the system make a choice. And once this choice is made, that value is updated, and that circle keeps moving on like any intelligent system interacting. It takes a choice, and then it evaluates its impact, and then it can see if the impact here is low, then maybe low risk is not needed. So it will stop conditioning on that condition only on food with high energy, and that will change the values of the different food or object it encounters, and then it should consume different ones, and that should update here, and so on. And along the way, all of the entire value of the interaction is also updated in here, which will tell in which direction we are going for the entire system. So how is that implemented? That's implemented by what we call an formation digital twin. It monitors the interaction of the agent with its environments. It has this kind of representation, and once there is an objective, the objective translates into conditioning on certain events or features, and then it provides the necessary calculation for the selection, the number of bits in selection, and the impact of the various selection. It can provide simulation, according to which the agent then decides which action to take, and the entire cycle keeps being increasing, and the AIDT all the time calculate this kind of information provided to the agent. So what we are currently focused on is understand how to mature that this kind of view, understand how to use machine learning, as I mentioned, to understand the dependencies between different parameters, because some of them might happen together. So this will reduce the information required to make a decision. Some of them will happen with less frequency, and so on. And what we are also trying is to develop other use cases. The one here is just an example, but the real ones is how to use that structure to make supply chain, to manage supply chain risks, to manage human-machine teaming, giving certain objectives. and then neonatal ICU risk events management for babies, and then the child abuse risk management. All of these are mentioned in the website in more details, and this is what we are trying to mature over time. Last slide, the perspective. The perspective is really to establish a new machine learning paradigm. This kind of structure that we just saw, this matrix with the Bayesian information, what differentiates it from machine learning, or what we hope we can show, it learns with much less data, like Bayesian in general. Doesn't need so many cases or data to learn from. The second advantage is it is transparent. You can trace every single change and where it did an impact, which is very challenging for machine learning decision making right now. The point about this kind of matrix that I think is interesting is that even if that matrix is 1,000 by 1,000, every single action reflects in there. So every single action can be traced to how it impacts every single parameter or feature in that matrix. And that is, we believe, something very valuable in understanding in medical applications, for example. The long term is that, I mean, we build these information digital twins, or what we call human digital twins, which are the same structure but in support of a human, to automate complex social interactions. And there is some concepts and explanation as well in our website. Thank you very much for your attention.
My name is Anton Kalonin, and I'm going to present our work on causal analysis of generic time series data applied for market prediction. The goal of our work is to provide the causal analytics framework for prediction oracle capable to provide predictions for price, volume, and risk for the purpose of automated active portfolio management. So we are collecting different sources of data from market, like exchanges, centralized exchanges, and decentralized exchanges like smart contracts, and media, like different social media feeds from Twitter and Reddit. This data is being preprocessed and turned into various metrics, like metrics derived from the market data, like different derivatives from price, like difference and local returns, and different sorts of imbalances computed from the sell and buy volumes and trade counts, ask and bid prices and volumes. And also we are computing metrics derived from social media, like sentiment, positive, negative, contradictiveness, and overall sentiment, and cognitive distortions known in cognitive behavioral therapy. And these predictions and these metrics are turned into predictions, and predictions are turned into the parameters used to identify the strategies for trading bots which are performing trading or market making activity, turning these parameters into the particular actions on the market, and then the data is returning to the market, affecting the markets, and we are continuing to run this circle. The goal of our causal analytics and predictive framework is become able to identify the patterns on the market. So in order to identify the patterns, we need to somehow symbolize the market states, like figuring out the particular situations on the market, like prices going up or prices going down, and price is crashing, and we need somehow identify what is up and what is down and what is the crash, so to speak, how much up is up and how much down is down. And one of the approaches for symbolization of the market states is figuring out specific parameters that can be bound to specific intervals. So values on one or another interval can correspond to symbols, and then we can further assemble the symbols into the associations of the symbols or states that might correspond to particular market conditions, like flat market or crashing market or market going up. So we can further can identify the sequences of market states usable for predicting the particular scenarios of market activity. Another source of data other than market data is media data. So we know that the emotions and manipulations are affecting the market. So here is the example of the Walmart fake news in respect to Litecoin, and on the right you can see the peak of the sentiment. Peak of the price caused by this false sentiment, and underneath you see the volume of the trades, first on buy and next on sell, based on this manipulative content. And all of these metrics, like market metrics and media metrics, are assembled into the so-called cube of data. So we are building three-dimensional cube where one dimension of the cube corresponds to markets, like trading pairs on certain exchanges and smart contracts, and our experimental setup involves 10 to 100 of different markets or trading pairs. And also on this dimension we can consider different news channels, like different feeds on Twitter or different subreddits on Reddit, and we are now analyzing about 100 of such channels. On the other dimension we can see different metrics. So some of the metrics are market metrics derived from the market data, like price derivatives, indicators, different imbalances based on the trade volumes and the order book volumes and price structure. And another metrics are sentiment or polarity or cognitive distortions extracted from the social media posts. And we have about 100 metrics computed from the market data and about 20 different metrics derived from the social media. So you can see that in overall we have about thousands of different metrics to analyze, and thousands of these metrics are distributed across the timeline. And then we can use the correlational analysis to align, to compute the mutual correlation between all of these different metrics with different time shifts, assuming that the correlation of two different functions with shift in time may point to the causal connection between the metric which is changing one step back in time before the other metric is changing one step forward in time. For example, on this synthetic example, we can see that the two synthetic indicators, like pumping and dumping indicator on the top, are correlated with the price difference. So we see the price on the second plot and the price difference on the third plot, and we correlate each of these synthetic pumping and dumping indicators with the price difference on the third plot. And underneath you see the heat map where the shifted price, the price price difference plot shifted 1 point back and correlated with the respective pumping or dumping indicator are reflecting in highly positive correlation and minus 1 point, 0.77, and highly negative correlation with dumping indicator at minus 0.77. So this high correlation cells on the heat map at minus 1 shift point are pointing to potential causal connections between respective source indicators like pumping and dumping and the target indicator, which is the price difference. So correlation is not causation, but temporal correlation is more like causation, or can be thought as a causation. And here you see non-synthetic kind of analysis on the same kind. On the left you see one particular cognitive distortion across different channels. channels are on the vertical axis, and you see there are different time shifts on the bottom, and at -1 shift here you can see some high and some high positive and negative correlations, pointing out that news communications on these particular channels might be affecting the price. On the right, you can see another shift of this three-dimensional data cube. So we have the shift fixed. So here is just single shift -1, and we consider multiple metrics and multiple channels. So the metrics are on the bottom, channels are on vertical axis, and you can see which of these metrics on which of these channels are highly correlated positively or negatively with the price difference. Another kind of example can be applied to the market data. So the first slide, the slide before was about the social media data, and here we have the correlation of the market data. On the left you see the single market, the BTC USDT in given case, and multiple metrics on the vertical axis and shifts on the bottom horizontal axis, and you can see that most of the metrics are correlated with the price at 0.0. So price is highly correlated with almost everything, and some of the metrics are highly correlated positively or negatively with price at +1 point. So price is causing changes in many things, but unfortunately you don't see any significant correlations at -1 point. So from market data perspective, here we can see that price is barely correlated with something before the actual price change, which makes the price prediction based on the market data more difficult than it might be thought based on the social media data, like we have seen just on the previous slide. And also on the right you can see that we can analyze this sort of correlations with different shifts, visualize it with bars, and further we can do the analysis in attempt to build what we call synthetic additive indicator. So we are trying to find the different metrics on market data and social media data which are having greatest correlation with the price if assembled together. So we are finding the combinations of the metrics that being added one to other provide higher correlation at -1 point, at -1 day or hour or minute shift against the target metric which is price. And here you can see the results of our experiments. On the left you can see our attempts to build synthetic market indicators based only on social media data. So on the left you see that we try to build synthetic indicator with different time shifts from -10 to +10, and each bar corresponds to the highest correlation that we can achieve between the price and the synthetic indicator assembled from multiple news feeds, multiple metrics from multiple social media channels with different sets of metrics. For example, at the bottom you see that we use sentiment data only. Next from the bottom here is corresponding to using only cognitive behavioral schemata, the cognitive distortions only, and then we can have sentiment and cognitive distortions, and sentiment and cognitive distortions, and counts of news per day. And you can see that in all of these cases the highest correlation can be achieved for this synthetic indicator at -1. So that means that there is something highly correlated with the price across multiple metrics that are assembled together, specifically day before the price changes. All analyses on the social media data have been done on the daily time series. What is interesting is that the sentiment only provides is sufficiently low correlation. It's just somewhere in between 0.5 and 0.6. But if you consider cognitive behavioral data or cognitive distortions metrics computed from social media, then you can see high correlation almost at 0.8. And if you add sentiment to cognitive distortions, you get up to 0.8, and adding counts of the news to that these metrics doesn't improve the quality as well. And by the way, if you start adding market data, it also doesn't improve quality, because on the right you can see the market analysis of the market data. So we are using the same kind of process, building what we call synthetic additive market indicator, assembling the metrics that have the highest correlations with the price into synthetic indicator, as long as adding them together increases the overall correlation with the price difference at the specified time shift. So here we can see that at daily sampling rate we have positive correlation at -1. It is not that high, it is just 0.2 and something. And then we have same amount of correlation at 0. So there is some I would say hope for being able to build some predictive algorithms based on this correlation, but it is not that I would say impressive as in case of the social media data. If you try to go down on time scale, so if you try to use more fine-grained temporal time series data with market parameters on hourly basis, you can see the picture is even worse. So on -1 shift, the correlation synthetic indicator can be built with pretty low positive correlation, while at the point of 0 and point of 1 shift, 1 hour shift, you get much higher correlations. So you can see that on the hourly scale, the price is rather driving the other metrics rather than some other metrics are driving the price. And if you move to the minutely data, then on minutely time series data, you can see that the correlation built at 0.8, the correlation, Pearson correlation at the level of -0.8 is taking place at +1 time shift. So again, so there is some strong correlation with some set of market parameters after the price change. So the price is causing these changes, and also some of the parameters are correlated with the price at 0 shift, and also only the 0 shift based correlation is found on the secondary data. So far that kind of analysis suggests that our further work will be focused primarily on making the price prediction based on the social media data.
Hello, I'm Howard Schneider from Toronto, Canada. I will be talking about analogical problem solving in the causal cognitive architecture. A comment I received was that there are so many equations in the paper and that they need a better explanation. Let me do that now. Okay, let's take the 10,000 meter view of the paper. Okay, to start our 10,000 meter view, let's go to the beginning and ask an important question. What are the mechanisms we can use to think, to make decisions? Well, there's symbolic logic, GOFI, good old-fashioned artificial intelligence. In theory, it should be able to do everything, although it hasn't worked out that great. Neural networks, artificial neural networks, spiking neural nets, have done some pretty amazing things in the last decade. There's other ways we can get intelligence from systems. I am using something I call navigation maps, both it's a symbolic structure with a lot of connectionism within it. Okay, what's a navigation map? Think of a roadmap in the pre-GPS era. Here there's a number of road maps that you can flip pages as you get to the borders of each page. This is the navigation map in my architecture. Instead of being made out of paper, it's made out of Python programming language using the NumPy library. It's a 6-dimensional structure. There's 3 spatial dimensions, X, Y, Z, and as well I'm using 3 non-spatial dimensions. Very important. Every module in the architecture uses navigation maps. There isn't just a special little navigation circuit and all sorts of other circuits. Everything uses navigation maps in my causal cognitive architecture. And indeed, my architecture is biologically inspired. Most invertebrates with their tiny little brains, as well as vertebrates, of course, use some sort of navigation system. All vertebrates, not just mammals, have some sort of formal navigation system, often very similar to the mammalian hippocampus. In my original causal cognitive architecture, I postulated that the rest of the mammalian brain, i.e. the cortex, it's just the hippocampus which has been duplicated a zillion times, and I assumed everything is navigation maps in our brains, and hence the basis of my architecture, and hence the basis that the navigation map is the fundamental data structure in the causal cognitive architecture. And then when you look at the equations, it makes a bit more sense. And what I found a few years ago was that there's feedback pathways in all the circuits already. Lots of feedback pathways in mammalian brain. But if we slightly enhance, let me get the laser here, if we slightly enhance this feedback pathway here, what happens is, and we feedback intermediate results and reoperate on them, causal behavior emerges, not pre-causal, which most animals have, but full causal behavior emerges, but also at the same time, you get psychotic-like conditions. Although 1% of the population suffers from schizophrenia, which is a huge number, actually, epidemiology shows 17% of the population at some point will have a psychotic-like reaction. These are massively big numbers that just don't really make sense compared to other illnesses. Plus, if you look at the animal world, although animals do get other psychiatric illnesses, they almost never get psychosis. Okay. While other animals don't seem to get psychosis, they don't seem to demonstrate full causal behavior either, including chimpanzees. Very good experiment where the chimpanzee can push food out of a stick. However, if a gravity trap is put in, there's very little causal understanding of the effect of gravity. The problem was solved in about 160 tries via association. Okay, so this is the causal cognitive architecture 1, and it's reflected in those equations. This is what's reflected in there. And it seemed to work okay for toy problems, but for example, the binding problem wasn't a philosophical problem. It was a real engineering problem making the system work well. So, the causal cognitive 2 emerged. The causal cognitive 2, which is reflected in the equations. As is reflected in the equations, the input sensory systems are individually mapped and matched against composite navigation maps, and the best matches for different systems are chosen, and then finally the best match is chosen, and then that becomes the system's perception of the sensory world, and then it's updated with the actual sensory information. And binding of the vari-sensory system occurs, and it solves a significant engineering problem, not just a philosophical problem, and the system seemed to work well. However, the philosophers never considered binding time. And this turned out to be a huge engineering problem too in the system. If we're running 30 sensory frames per second, you get a multitude of navigation maps that have to be bound. It becomes a mess. So as a result, the CCA3 was created, where we bind not only space, but we bind time as well. We generate motion prediction vectors, and then we bind these vectors as spatial data rather than as temporal data, and it has worked out great. And this is reflected in those equations. And hopefully this explanation with these figures makes a bit more sense when working through the equations. Okay, let's take a look at this equation. It's the information has gone through the causal cognitive architecture in equations 1 to 77 so far. We get to equation 78. WNM is the working navigation map. That's the navigation map upon which the system has attention, upon which it's going to do operations. Working primitives are also navigation maps, which is shown in the paper and explained. And primitives instruct the navigation module to perform operations on the navigation map. And again, it's array operations on top of each other. And this navigation module dot apply primitive is pseudocode for an algorithm which applies the working primitive map on the working navigation map, and it produces an action. And what will happen, of course, depends on the contents of the working navigation map and depends on the content of the working primitive. And as I mentioned before, what proved fascinating is if, for example, on that operation that was done before, if you get the action, if that action doesn't really give something useful or meaningful, what happens is, for example, it ends up not having a move thing. It's not an actionable action. Then what we do is these equations 84 and 85, we feed there's already feedback pathways throughout the mammalian brain. We just enhance the feedback pathways a little bit, feedback the intermediate results of the navigation module to the sensory system, and then in the next cognitive cycle, that's treated as a new sensory thing. So you can reoperate on the intermediate results, and as I shown last year and the year before, is this results in causal behavior. It also results in psychotic it results in a vulnerability to psychosis as well. Okay, the work up to here, i.e. the work up to equation 85 has already been presented. However, the reason the equations are listed and they are described briefly, as well as with more information available in the references. The reason the equations are there is because the next set of equations, the new work which I'm presenting here, really won't make sense unless you have this introduction, which hopefully this small video makes a bit clearer. Okay, I just showed you the causal cognitive architecture and how we can feedback the intermediate results and then they get reprocessed, and often that can allow causal results. However, in reality, very often not that much usefulness occurs. What I found about half a year ago is that a small tweak to the core algorithms in the architecture gives a much better result in processing intermediate results and effectively produces analogical problem-solving abilities. I won't have enough time to go through every single equation fully here, but I will show with the example. And again, what is happening here is that we're just we take what has happened, we feed it back where we've already been doing that to store it, but then also we match it against another map in the causal memory module. And then we ask, in the past, what happened? What was the next step after that? So then we look at the next step, and then we subtract the next step from the current state, and then that difference we add to the original working navigation map, and as a result, you get an analogical result. And let me show you this in an example. I just want to point out something very important. the analogical inductive abilities are now a core mechanism of this architecture. It's not a special algorithm that the architecture calls up, oh, when it's writing an IQ test, how to do analogies. No, no, no. It's a core ubiquitous mechanism of the architecture now. I took this from Cholet's abstraction and reasoning corpus. I simplified it somewhat, of course, which is very useful when you want an example that's simple to show a system that doesn't have, for example, the real world knowledge that perhaps a human might have, and you want to see how good is it. Cholet was trying to show how intelligent it is. It's an excellent example, I think, for this purpose. Okay, imagine there's a video camera attached to the architecture and some video information comes in. It sees some lines in the environment and it sees lines in these areas, in these spatial areas. Okay, what to make of it? What action next to do? Okay, well, the best matching navigation map from the causal memory module now becomes the new working navigation map, WNM, and we've already fed back the old map, and you can look at the equation, show this. Okay, and in the next equation, what we're doing is we follow the link that's showing in the past, that working navigation map, WNM, what other map did it link to? And it links to this navigation map. And so this gets the current attention of the system. Okay, so we take the difference between that working map and then the one it linked to, and we get this here. And then we add it to the original working navigation map, and we get this, which with the lines removed is this. So then this is the result. The system saw Cholet's question, so to speak, in his ARC test, and this is the answer it's giving. And it's quite a reasonable answer given the logic that it followed. And it might prove useful. It's useful, it can be used. If it's not useful, the intermediate results can be recycled again. And this actually, giving the system inductive analogical abilities actually is a very, very useful property. And it may not look like it. It seems like, oh, we just moved around some navigation maps, i.e. arrays, but actually induction by analogy, very strictly mathematically has occurred. For example, if we have object X and object Y, and X and Y both have these properties A1, A2, A3 up to AN, and they have these properties in common, and then we see that object Y also has property B. Therefore, object X has property B, induction by analogy. And again, the purpose of this paper was not to show some super great way for AI systems to solve analogies, but rather that if we model the mammalian brain, as I did, causal abilities and psychosis emerge, and then again, with some very tiny evolutionary changes, induction by analogy emerges, but not as a separate module or separate ability, but as a core ubiquitous mechanism. Thank you so very much for watching this video. If anyone would like to get in contact with me, my email address is there as well as on the paper. Thank you again. Bye-bye.
Dear ladies and gentlemen, my name is Agi, and I am going to tell you about our work that we committed to Agi conference. So this work is called MARTI4, the new model of human brain considering neocortex and basal ganglia, which learns to play Atari game by reinforcement learning on a single CPU. And the authors are Igor Pivovarov and Sergei Shumsky. So talk structure will be, I'll describe the main ideas of deep control architecture, which is inspired by the brain. I'll briefly describe the MARTI model and how we test it on OpenAI Gym and what are the results. So it is well known that brain is the main part of a brain, which is responsible for rational logical thinking, is a neocortex. And the neocortex is widely modeled by neural networks, which are commonly used now. But the part of the brain responsible for emotions and behavior is limbic brain and basal ganglia in its center. And also there's a big part of a brain which is called cerebellum, which is responsible for routine movements. So neocortex consists of is organized, neurons of neocortex organized in groups, which is called cortical columns. There are a lot of cortical columns. Human brain has around several millions of mini columns, which are united in cortical columns. And in our model and in some other models, which we are citing, cortical column is considered to be a prediction model, single prediction model, which receives data and makes some predictions. And neocortex is considered to be an ensemble of predicting models. Thalamus is a central part of the brain which is responsible for distribution of information. It proceeds information from sensory motor to neocortex and back, and it is regulated by basal ganglia. And basal ganglia is in the center of limbic brain. So this is a command center which really is responsible for taking decisions. It's a most powerful braking system in the brain. It inhibits most of all thalamocortical connections and disinhibits some of them, which is a way of regulation of this neocortex work. And the part of this basal ganglia which is connected directly to the neocortex is striatum. So we model this part of striatum. So our model consists of thalamus and let's say thalamus, which provide information for different columns, and we have this striatum which models, which regulates these columns and the connections between columns and thalamus, and also the part of main idea of deep control architecture is that columns are growing in hierarchical level. So upper columns look on the columns on the lower level and try to analyze and predict their state. So this is the main idea. So main ideas of deep control architecture are that neocortex is a building world model and making predictions. Cortical column is a single model which make predictions, and we use a symbolic parser as a model for this cortical column, which I describe later. So there is a hierarchy of columns, and this is a main idea. And basal ganglia is a model that orchestrates all this ensemble of columns and choose predictions which are really will be implemented. So we'll take a closer look on MARTI, which is implementation of this deep control architecture, implementation in code. So MARTI is a hybrid vector symbolic artificial intelligence, which is hierarchical, modular, and asynchronic, and it is specially designed to implement goal-based behavior. So as an input, MARTI takes digital vectors of any nature. So there's a digital vector of any size, and it has some sensor data, current action data, and the reward, which it receives from the environment. Thalamus processes this input vector into smaller vectors and give it to connectors or coders, we can call coders. And the main task of this coder is to collect enough data and to clusterize it. And after clusterization, all these vectors are clustered into different clusters, and you can think about each cluster as a letter. So let's say if we have this 30 clusters, vector set divided on 30 clusters, then we have 30 letters. And then these letters are passed by to the parsers. So above these coders, Thalamus creates symbolic parsers, which process these letters from coders. And these parsers process letters, collecting the correlation information, the reward information, and try to predict next most probable letter, which will be. Also, Thalamus creates a action encoder which code only the action information and encodes it into a letter of action. And with all these letters, Thalamus creates next level of parsers, which we call action parsers, that have a complicated letter as an input, which is a concatenation of letters of lower level. So action parsers are also parsing these letters, gathering words from these letters, and have the correlation table, which stores the information of correlation between letters, and the most often letters that going one after another are combined into words. And also it stores the information about rewords and try to calculate the value function of each state, if each word in its language, let's say. And these value functions are used to predict the next most valuable step for this action parser. Basal ganglia is a model which after all these parsers made the predictions, it tries to find out the most valuable prediction from the group. And the most valuable is, there are many ways to define it, but in MARTI4, it is considered as a prediction that is the moment that most parsers are positive for. So in this case, this is moment U, which most parsers consider this positive moment. And when this selection is made, Thalamus processes the winner parser and takes his prediction as an action to the environment and give it back in a decoded value. So MARTI receives two types of rewards. So one of it is the external reward, which is normal for every reinforcement learning environment. It is received when you win the game or lose the game or making something right, and so this reward is given by Stratum to all the parsers. And another type of reward is called internal rewards. It is based on surprise feeling. We use this situation parsers, which try to understand which is most probable continuation of this situation, but sometimes they have some unexpected improvement of their predictions. And in that case, we call it the surprise feeling. And when several situation parsers have this surprise feeling, basal ganglia understands that something good happened, and this is rewarded. So in case of MARTI, this means that something good was done really, but no external reward for the moment, still not given for the moment. So to summarize MARTI, there is a multi-agent model. Each column can be considered like a small agent, which has this part of the picture, and based on its information, it makes some predictions, and it explores the causality and makes these predictions, and final decision is made on the ensemble of these agents. Current version is written on Java. It works on a single CPU and learns in real time. And we test it on an OpenAI gym. OpenAI gym is a set of different environments used for RL, and specifically we use the Pong game, which is a ping pong game. We use it 500 steps long, and MARTI receives the RAM state of Atari, 100 bytes, and an action as an input and reward, and output an action of one number. And so here you can see the demonstration of results. So we see that we see that when Martin moves randomly, it usually from the very beginning, it usually loses around 9 to 0. And here you can see the Marty after 500 games learned, so it movements quite more, makes sense more, and it still loses, but not at so big levels, we'll say. And so we use two types of estimating the results. First is the game of 500 steps, which I showed you previously. And in this game, after 500 games, Marty average difference of win to lose goals increase from -9 to -3, around that, after 500 games. And if we let Marty to play the game up to 21 goals without any restriction to steps, so it loses with a difference around -15, while the random is around -20. And of course, the best models use now winning like a 21 to 0, but this is the level we are going to achieve. So as a conclusion, we present deep control architecture, a hybrid vector symbolic ML architecture, which is implemented into Marty. There's a new model of brain with a neocortex and basal ganglia, which is capable to learn in reinforced environments. And one of our goals was to show the role and potential mechanism of basal ganglia in human brain in the whole decision process. So thank you very much for your attention. And I would like to make a disclaimer that this this work was made by authors solely on their free time. And nevertheless, Sergei Shumsky and me works in several institutes. This work was made in free time without any support of any participation of any entity. Thank you very much. I'd like to thank you very much for your attention, and we'll be happy to answer any questions. Thank you.